Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. In the last lecture, we discussed certain examples and features of having different I/O devices. We considered an example of mapping the input device with reference to a Falcon A processor. Now we also discussed the concept of data bus multiplexing and said that we could use the address space of the available CPU more efficiently, and therefore the alignment of addresses is not required. However, using data bus multiplexing implies additional hardware. Now it depends whether we want additional hardware or we want just economy of the addressable space. Finally, we discussed a generic I/O interface where we indicated registers with arbitrary addresses, and finally we ended up with a typical I/O interface used for printers, that is for Centronics interface. Today we will continue from that point, discuss the Centronics interface in a little bit more detail and apply the Centronics interface with reference to some typical examples. Let us have a look on the next two tables to illustrate the important concepts of this Centronics interface. The table shows the Centronics parallel printer interface. For the sake of simplicity, the power and ground signals are not indicated in the table. The first column shows the signal name. As an example, the first signal is the data signal. D with angle brackets 0 to 7 indicates 1 byte of data. The second column indicates the direction or the signal with reference to the printer. Note that in the previous examples we have been referring the direction with reference to CPU. In this column, the direction of data or signal flow is indicated with reference to the printer. As an example, the data is indicated as an input. This is input for the printer. However, this has been outputted by CPU. So CPU, through its data bus and the interface, has sent this data, and this would be accepted as input by the printer. The next column shows a reference summary of the functions. The fourth column indicates the pin numbers on the CPU side. You remember we said that it is a 25-pin connector on the CPU side. As an example, the data is on pin number 2 up to 9. The last column indicates the pin number with respect to the printer side. And note that on the printer side, we have a 36-pin connector. In most of the cases, the pin numbers in column 4 and 5 are the same, except for certain cases. As an example, you will see that the initialize signal is available on pin number 16 on the CPU side, whereas it is pin number 31 on the printer side. An important overview of different signals should be noted again. In the last lecture, we explained the strobe signal. The strobe signal, when it is low, would activate the data bus from the CPU side. So typically the default value should be high, and low value would indicate read in of data by the printer. We also explained in the last lecture the timing requirements for this strobe signal. Altogether, a minimum time of 0.5 microsecond should be the value for which it is low, but it should be preceded by 0.5 microsecond, and then after becoming high again, it should be also 0.5 microsecond. So therefore, the total width or total timing requirement would be 1.5 microsecond at least for the strobe signal. The acknowledge signal is also active low. Therefore, when it is low, data would be received and the printer would be ready to accept the next data. So its default value is high. Now busy is one of the very important status signal which is an output with reference to the printer. So this would be data input available on the CPU side. Its bit low is the default value, and when it is high, it would be busy. So therefore, it would be high during data transfer or when the printer is busy. So we'll see in the forthcoming examples that the busy signal needs to be checked by CPU, and only when it is corresponding to a high signal, the data would not be available and it needs to be low. So when it is low, only then CPU can send data to the printer. Another important signal is the initialize signal, and low value would correspond to the printer controller is reset to its initial state and the print buffer is cleared. High would be the default value. Similarly, we have other signals like select in and select, and you can read more about these signals in the table. The next table shows the Centronics bit assignment for I/O ports. The first column indicates the logical address. So in this column we have three logical addresses, 0, 1 and 2. Physically, for our previous example of Falcon processor, each logical address may correspond to two physical addresses corresponding to 1 byte each. So 0 logical address corresponds to the 8-bit output port for data. So we'll use 0 as data port. Then 1 is for the status port and 2 is for the control port. The next 8 columns indicate each bit. For logical address 0, the assignment is from D0 up to D7 corresponding to 8 bits of data. At logical address, we have the status signal available like busy and the error signal. Least significant bits 0, 1 and 2 are unused. For the control logical address 2, the bits 7 and 6 are unused. Bit 5 indicates the direction, and usually it should be low if CPU has to send data to the printer. Similarly, bit 4 indicates an interrupt request enable, and in the case of a normal programming mode which we have discussed so far, this should also be set to 0. Similarly, the bit 2 at logical address 2 should be initialized to 0 to start the activity of the printer. In the last lecture, we had discussed a hardware interface for the case of Falcon A processor. We said that using the Centronics interface, we want to transfer data from CPU of Falcon A to the printer. We use the addresses arbitrarily as 56, 58, and 60 in decimal. So we will say that 56 corresponds to the data port, then similarly 58 would correspond to the control port, and 60 would correspond to the status port. Now we implemented this by using the 8 address lines, which correspond to the address lines or lower bits on the address bus of the Falcon processor, and with the corresponding hardware, we assume that the same interface is available now for the following examples. In the next example, we say that using these addresses available to us for interfacing Falcon A with the printer using Centronics interface, we need to transfer now, instead of one character, the 80 characters from CPU to the printer. And we are supposed to look into the flowchart and then the corresponding assembly language program. So again, the problem is very simple. We say use the Centronics interface, which has been developed as far as the hardware is concerned in the last example, and I'll just show you for quick reference also today. And using this hardware interface, we just start sending the 80 characters in ASCII from CPU to the printer. Let us see at the corresponding flowchart and the program for this particular example. For quick reference, in this slide, the address decoder for 3 parallel ports for the Falcon A at addresses 38 hex, 3A hex, and 3C hex is shown. These addresses in decimal correspond to 56, 58, and 60. The example which we are going to discuss now is, we assume that a Centronics parallel printer is interfaced to the Falcon A processor. As I have just shown, we are supposed to write an assembly program to send an 80 character line to the printer. Assume that the line of characters is stored in the memory starting at address 1024. The flowchart for this particular example is shown in the figure. The first thing that needs to be done is the initialization of the printer. This means that a reset command should be sent to the printer. Using the information given in the table which has been shown earlier, this can be done by writing a 0 to bit 2, that is the initialize low signal of the control register having logical address 2. In our example, this maps onto address 60 of the Falcon A. Remember to set this bit to a logical 1 for normal operation of the printer. Then we make the strobe signal high by placing a logic 1 in bit 0 of the control register. Bit 1 and bit 3 should be 0 because we want to activate auto line feed and keep the printer in selected mode. Additionally, bit 4 and bit 5 should be 0 so that interrupts are disabled and the unidirectional data flow from CPU to printer is selected. The complete control word in binary would become 0, 0, 0, 0, 0, 0, 0, 1, and this value has been assigned to the variable reset in our program. The following instruction pair performs the reset operation. Move immediate R1, reset. As we said, the value of reset in this case is 0, 1. Out R1 to control port. So control port address in this example has been set to 60. As it is given that the starting address of the printer buffer is 1024, so we place this address in register R5. The mask to test the busy flag is placed in register R3. The value for the mask is 80 hex. This corresponds to a logic 1 in bit 7 and logic zeros elsewhere for the status register having address 58, which is logical 1. Then the program enters a loop called the polling loop. This tests the status of the printer, if it is available or otherwise if it is busy. If the printer is busy, the loop repeats itself. Following three instructions form the polling loop, which could be read as in R1, status port and R1, R1, R3. This instruction would AND R1 and R3, the contents of R1 register with R3. If the result is not 0, it would jump to the label again, which would mean again it would read the status port and see if the status has changed or not. So this loop would continue. It would poll and ask the printer, are you ready or are you busy? If it is busy, then it would wait till it becomes available. The status of the printer is placed in register R1 and bit 7 is tested for a logic 1. If not so, the program repeats the status check operation. When the printer is ready to accept a new character, it clears bit 7, that is the busy bit of the status register. At this time, the program picks the next character from the memory and sends it to the printer. The strobe line is activated and then it is deactivated to generate the necessary pulse on this input of the printer. Finally, the buffer pointer is advanced. The loop counter is decremented and the process repeats itself. When all the characters have been printed, the program halts. Now this example is illustrative of what we have discussed earlier. Firstly, it explains the use of Centronics interface, and you should by now understand very clearly that for this interface we have three logical ports, and each one logically we just call it logical port 0, 1 or 2. We just through address decoders just numbered with arbitrary addresses. In the example, we just used addresses 56, 58, and 60 consecutively for data, status, and control ports. Now then, we considered a very important concept of what we called polling. And in polling, we said that the interaction of CPU with the I/O port is a constant questioning. So CPU asks, are you busy or are you available? So looking at the busy signal, which is a status signal available on the status port, the CPU decides whether to send data or not. Now in the example, if we extend and facilitate that the printer also has a buffer. Instead of checking the status after sending every character, then we would need to check the status when the buffer is full, and we could generate a status signal which would correspond to buffer full instead of just having sent a character and checking the busy status. We will illustrate this principle in one of the following examples. Now, this brings us to the point where we could say that the transfer of data from CPU to the I/O device could be done in 3 different modes. The first mode is the programmed I/O. So far we have been discussing these examples. In programmed I/O, the operation or the transfer of data from CPU to the I/O device is executed under the control of a program. So CPU is tightly bound and the I/O device is constantly, for example, polled, and in the previous examples which we have discussed so far, it is an example of a programmed I/O. So we have a program residing in the CPU which interacts with the I/O device. Now, as we have seen till now, this might not be the most efficient way. This could be quite inefficient to transfer data from CPU to the I/O device. Now, later on, we'll discuss 2 other modes of a data transfer, which could be interrupt-driven I/O and the DMA or direct memory access. These 2 modes of transfer we will discuss in the following lectures. However, today we will take some more examples and illustrate the programmed I/O concepts. Let us have a look at the next example, where we will also see and keep a track of the time consumed in different instructions and see that how would be the data transfer from CPU to the I/O device, and check whether it is efficiently transferred or a lot of time is wasted in this process. Let us go through the next slide to see this example. The main loop of the program given in one of the earlier examples is shown for quick reference. This executes 80 times to transfer 80 characters. Additionally, you will just see in the last column within square brackets a number. This number indicates the number of clock cycles required for execution of that particular instruction. This portion of the program is shown with the execution time of each instruction listed. The number shown is for a unibus CPU implementation for Falcon A, and these numbers could be fetched from one of the earlier table which we had shown for Falcon A instruction set. A number of things should be noted. Assuming that the output at the hardware pins changes at the end of the I/O wired bus cycle, the strobe signal will go from logic 1 to logic 0 at the end of the instruction pair given by move immediate R1, strobe low. This requires 2 clock cycles. Out R1 control port, and this output would require 3 clock cycles. The execution time for these 2 instructions is 2 plus 3, 5 clock periods. Therefore, the strobe stays for at least 5 clock periods. That is, during these 2 instructions, if a 10 MHz Falcon A CPU is assumed, it would correspond to 500 nanoseconds, which is 0.5 microseconds. Since the data to be sent to the printer is given by CPU with the two instructions load R1, comma, within square brackets R5 and out R1, comma, data port, which are before the first move immediate instruction. The printer's data setup time requirement is therefore satisfied as long as we do not increase the clock frequency beyond 10 MHz. After these two instructions, the next two instructions are just repeated, given in the main program, and it would set the strobe to logic 1 again. These instructions are move immediate R1, strobe high, and this requires 2 clock cycles, and out R1 control port would require 3 clock cycles. Therefore, these two instructions also take 5 clock periods corresponding to 0.5 microseconds to execute. Thus, the timing requirement of the strobe pulse width will also be satisfied as long as we do not increase the clock frequency beyond 10 MHz. In case the frequency is greater than 10 MHz, other instructions would be required to be inserted between these two pairs of instructions. The printer's data hold time requirement is easily satisfied because there are a number of instructions after this out instruction which do not change the control port, and the character value is already present in the data register within the interface since the end of the out instruction. Now, the second important point to be noticed is the 3 instructions given with label again in R1 status port and R1, R1, R3 and jump not 0 R1 to again corresponds to what is called a polling loop. The process of periodically checking the status of a device to see if it is ready for the next I/O operation is called polling. It is the simplest way for an I/O device to communicate with the CPU. The device indicates its readiness by setting certain bits in a status register. The CPU can read these bits to get information about the device. Thus, the CPU does all the work and controls all the activities. The polling loop given above takes 10 clock periods if we assume a 10 MHz clock. One pass of the main loop takes a total of, you can just add up these values corresponding to the table, and this gives 38 clock periods, and which corresponds to 3.8 microseconds. This is the time that the CPU takes to send one character from CPU to the printer. If we assume that 1000 characters per second are sent from CPU to the printer, that is, printer has a speed of 1000 characters per second, then in every 1 millisecond we can send a character. So after sending a character in just around 3.8 microsecond, approximately 4 microsecond, the CPU will wait for remaining 996 microseconds before it can send the next character to the printer. This implies that the polling loop will be executed about 996 times for each character. This is indeed a very inefficient way of sending characters to the printer. An improved way of doing this would be to include a memory of suitable size within the printer, and as we just said, this would be acting as a buffer or a temporary storage for the data coming from CPU. The CPU can fill this buffer in a single burst at its own speed and then do something else, while the printer picks up one character at a time from this buffer and prints it at its own speed. This is exactly the situation with today's printers. The task of generating the strobe pulse will also be done by the electronic circuits within the printers. In effect, a dedicated process within the printer would do this job. However, if the buffer within the printer fills up, the CPU will still not be able to transfer additional data to the printer. A different handshaking scheme will then be needed to make the CPU communicate asynchronously with the buffer in the printer, which would result in an inefficient operation again. Now assume that the printer has a FIFO type of buffer, that is first in, first output buffer with a size of 64 bytes, which could be filled by the CPU in a burst. When one or more character values are present in the buffer, the printer will pick up one value at a time and print it. Remember, we have 1,000 characters per second printer, so it takes 1 millisecond to print the character. The program shown previously in the example is now modified and is indicated in this slide. For this situation, with the assumptions which we have made earlier, you can immediately see that the time has been reduced from 38 clock periods to 28 clock periods. However, note that while the instructions for generating strobe pulse have been eliminated, the polling loop is still there. This is necessary because the busy signal will still be present, although it will have a different meaning now. In this case, busy will mean that the buffer within the printer is full and it cannot accept additional bytes. The main loop shown in the program has now an execution time of 2.8 microsecond, assuming a speed of the clock as 10 megahertz. The polling loop still takes 10 clock periods, which is 1 microsecond. Assuming that this program starts when the buffer in the printer is empty, the outer loop will execute 64 times before the CPU encounters a busy condition. After that, the situation will be the same as in the previous case. The polling loop will execute for about 996 times before busy goes to logic 0. This situation will persist for the remaining 16 characters. Remember, we are sending an 80 character line to the printer. One could argue that the problem can be solved by increasing the buffer size to more than 80 bytes. Well, first of all, memory is not free, so a large buffer will increase the cost of the printer. Even if we are willing to pay more for an improved printer, the larger buffer will still fill up whenever the number of characters is more than the buffer size. Then what happens? It's again the same story. So polling as such is not a very efficient way of transfer in end effect. With the help of our previous examples, we have illustrated the concept of programmed I/O. We have seen that under the control of program, running in CPU, there is an interaction between CPU and I/O. The I/O device is constantly being polled. The polling loop is the basic key concept that CPU asks, are you ready to accept data or not? And through this polling loop, when the device is available, it's not busy, then data is transferred. Now, this is not a very efficient method of transferring data from CPU to the device. Now, we have also illustrated that if we could have a buffer of appropriate size available in the device, this particular polling or transfer of data could be made more efficient. However, the problem still lies with the technique itself. So, the polling technique or the programmed I/O technique is not very efficient, and it does not utilize the CPU time efficiently for transferring of data from CPU to the I/O. The overheads are large. So the actual transfer might require just a few milliseconds, but on top of that, just constantly watching the status and looking for the availability of the I/O device, that is an overhead, and that overhead may exceed beyond limits. This was realized long ago, and therefore the designers, they designed the technique of what is called the interrupt-driven I/O. This would be our topic in the next lecture. However, for the remaining time for today, we still would like to discuss some more examples of the programmed I/O. We will take a couple of examples from your textbook with the example SRC processor, and you will see that SRC processor is using memory mapped I/O, whereas the Falcon A processor, which we have discussed so far, is a non-memory mapped technique. So both are basically programmed I/O examples. We are going to discuss some more examples similar to what we have done previously. However, the processor now would be SRC instead of Falcon A. The first example illustrates how to output a single character, bit 31, that is the most significant bit of the status register, which we just call costat, corresponding to character output status, is to be tested for the output device to be ready. This bit value 1 would indicate that the output device is ready, and 0 would indicate not ready status. The first instruction stores the value of the branch target corresponding to label weight in the register R3. The second instruction places the character for output in register R2. The next two instructions form a loop to test the ready status. The loop repeats itself until ready is 1. The next instruction places the character in C out using the store instruction. The ready test loop may be executed many times if the device is slow. As an example, for a printer with a speed of 1000 characters per second, ready would be 0 for 1 millisecond for every printed character. This would amount to 100,000 instructions for a 100 MIPS processor. In this case, polling mode, processor would remain idle and would do nothing, which otherwise
could have been used for other tasks. The second example shows how to output a line printer. In a line, 80 characters are assumed. The device has an 80-character buffer. Characters are sent to the line printer similar to the character interface in the previous example. However, an additional control signal is used to print the line after all the 80 characters have been sent. The initial 3 instructions initialize 3 quantities, that is, buffer, which is a pointer to the character buffer area, a character count, which in this example is 80, and the branch target label, which is weight for this example. There are 2 nested loops starting at this label weight. The first loop checks for ready status. The other loop outputs a character, increments the buffer pointer, and therefore decrements the register corresponding to the number of characters left to be printed. This repeats till the contents of this register become 0. The last 2 instructions correspond to print the line. The total number of instructions to print one line would then be 3, the initial instructions, plus 80 into 7 instructions per character, and 80 is the number of characters, plus 2, which corresponds to 565. Assuming no wait and a 100 MIPS processor, 80 bytes would be transferred in 5.65 microseconds, which corresponds to a bandwidth of 14.2 megabytes per second. This high rate burst of data transfer is followed by a line printing corresponding to about 80 millisecond for a 1000 CPS printer. So we see the average rate would be only a little less than 1000 bytes per second.
The next slide shows an example of a programmed I/O driver for 32 character input devices. The register R0 is the working register. R1 stores a character into the selected buffer. R2, the indices are stored as CIN and CICTL pairs for I/O registers, and buffer pointer and done are the status conditions. That pair controls the input lines. R3 equal to 1 at the end of a pass only if no device is active. Instead of just going through the program line by line, just go through this program and see that this program actually is similar to what we have done for the inputting from Falcon, except that now the load and the store instructions are used instead of input and output, because this particular processor SRC utilizes the corresponding memory mapped I/O. Now the examples for SRC which we have discussed are similar to the examples which we discussed with Falcon A. The first example of the book indicates how to read a character. Now for a character, just like the busy signal, in this case we looked for the ready signal. When the ready signal is activated, then CPU sends the corresponding data to the output. We also discussed one example for inputting the characters, and in this case the instruction set is different, the address width is different, the number of lines on the address is different. So we just considered different registers available corresponding to the status port, corresponding to the control port, and corresponding to the data port. And these three ports would be used in all cases, whether it is an input device or an output device. So in the case of a programmed I/O, the basic concept boils down to a very simple thing, that the CPU would interrogate the I/O device, check if it is ready for transfer of data, and this would be done by status port. For the status port, the address would be available and appropriate decoding would be required through the techniques which we have discussed for address decoding. We can assign some logical numbers as logical ports for this. We can call this as a status port. Then the control signal needs to be activated by the CPU. The CPU would send the control signals on the control bus. Some of these control signals would be used by the I/O device for the address decoder. Now, if it is a memory mapped device, then it would utilize the address space corresponding to the memory, and the control signal would be memory read and memory write. If it is a non-memory mapped device, then correspondingly the control signals would be I/O read and I/O write. And the third logical address would be the actual data. So if it is the device for an output with reference to CPU, the CPU would define a port and send a data to this logical address which defines the data output from CPU point of view. And if it is an input, this would correspond to reading data from the peripheral device. So the concept is very simple. In the case of programmed I/O, the key concept is the polling. So through the program, a constant interaction would take place, the status check would be there, and based on the status check, the corresponding data would be transferred. To increase the efficiency of the programmed I/O, the buffers are introduced, and these buffers would be a part of the peripheral device usually. Now this buffer, if it is just a simple memory, then it is a slave to CPU. More interaction could be achieved if we could introduce activity and have another CPU chip within the peripheral device. A lot of activity could be taken over by the peripheral device. So a lot of work which previously was done by the CPU would be done by the processor within the peripheral device. Now, we have just illustrated the concepts through very simple examples. In practice, the same concepts could be augmented by more complicated programs and more complicated examples. Now, finally, we'll say that the efficiency of programmed I/O could be increased, but still the overheads could not be totally eliminated. And the main CPU still has a lot of burden of status check. And in the next lecture, we will discuss the interrupt-driven I/O devices. The concept would be very simple, that if the device is ready, then it would just call the CPU's attention, it would interrupt the CPU and ask for the service from the CPU. These concepts we are going to discuss in more detail in the next lecture. Today we'll stop at this point of time with the programmed I/O, and we will discuss the interrupt-driven I/O next time. Till next time, Allah Hafiz.